Jai Hind friends, I am Himanshu Tripathi, and here in this video I am going to discuss that how we can write assembly language program for 8051 microcontroller on our computer. Because I believe in this motto that if we are learning programming, then we should be able to execute those programs that we are writing. So it is my advice to all my students that if you want to learn programming, whatever the language is, it may be assembly, C or any other language, please write your programs on your computer using a particular IDE or any specific program so that you may be able to run your program and you may be able to see or understand that how your program is working. This will give you a clear understanding of any programming language. Since we are concerned about 8051 assembly language programming, so we will see that which tool is applicable or which tool is most suitable to write the programs so that we can practice well the assembly language programming of 8051 microcontroller. So here on my screen, I am going to the Google and the tool name is KEIL Microvision, KEIL UVISION. So if I am searching this KEIL Microvision, I am getting these search results. The very first one is Microvision IDE. Let me click on this Microvision IDE icon, and here you can see that lots of things are written about the Microvision IDE. It combines the project management, runtime environment, build facilities, source code editing, and program debugging in a single powerful environment. Instead, it is a very powerful environment. Generally, as experienced embedded developer, KEIL Microvision is used to develop the softwares or the program or firmware for the ARM family members of microcontrollers. But here we are basically looking for assembler or compiler for C language or assembly language, assembler for assembly language and compiler for C language, which is most suitable for 8051 microcontroller. So at the end of this page, here is the download link, and by using this download link, I'll click on the C51. This is a dedicated compiler and assembler for 8051 microcontroller. So this is the landing page of C51, and here you can see you have to provide your first name, last name, email, company, job titles and details, and submit this request, and you will get a executable file for C51 or KEIL Microvision C51 IDE. This is completely free of cost and you can download it very easily, and installation process is also very simple. You need to follow the prompt for the installation, and this software will be installed or IDE will be installed in your computer. So I have already installed this KEIL Microvision IDE, and when I open this KEIL Microvision IDE, this is my blank prompt for this IDE. In your case, there might be some sample project or hello world project. So if you want to close that project, you can go into the project section and you can select this close project option. So I've already closed any of the existing project, so there's no need to close any project for me at this time. So I'll quickly show you the way how you can make a project using KEIL Microvision IDE, and you may be able to write assembly language programming using this IDE. To make a project, I'll click on the project option of this Microvision IDE, and here I am clicking on new Microvision project. So when I am clicking on new Microvision project, you may go into any folder of your computer. So here inside my computer 8051 assembly language folder is here, and here I am making a new folder and I am naming this folder is test1. Now I am inside this test1 folder, and here I am giving the name of my project. So my name of my project is square wave. Our motive of this program that we want to generate a square wave from any particular GPIO pin of 8051 microcontroller. So I am naming my project as square wave, and in the bottom you can see that we are saving this as a .uv project or .uv projx. So there is no need to do anything. I've provided the file name and I click on save. The next step, this IDE is asking me to provide the name of microcontroller for which I am involved in the development. So here you can see number of companies and number of microcontrollers from different companies are available, and you may develop the softwares or firmwares for those microcontrollers. So we are going to work with 8051 variant of microcontroller, and this variant is from Atmel company, and the name of this microcontroller is AT89C51. So this is AT89C51. So AT stands for Atmel, 89C51 is the series of microcontroller. Now this Atmel company is also known as Microchip because it is a part of Microchip. So here you may be able to see the name Microchip instead of Atmel. So I am selecting this AT89C51 microcontroller, and just after the selection I may be able to see the specifications of this 8051 microcontroller. If I am reading these specification, it is 8051 based fully static 24 megahertz CMOS controller. Like the maximum crystal frequency that we can provide this to this microcontroller is 24 megahertz. Generally, if you are looking into the data sheet of 8051 microcontroller, you may find the operating frequencies is ranged from 0 to 24 megahertz. Like if you are putting operating frequency low, then your processor is executing slow, and if you are increasing the operating frequency towards its maximum limit, and the maximum limit for 8051 microcontroller is 24 megahertz, as we are increasing the frequency of microcontroller, the speed of instruction execution is increasing. But there is a trade-off. Like if we are increasing the speed, the power consumption is also going to increase. So to get the optimum performance or the best balanced performance, it is tried and tested that 8051 microcontroller works fine around 12 megahertz of frequency. So in most of our application, we use 12 megahertz crystal for designing 8051 based development boards or 8051 based projects. For serial communication purpose, we need to generate baud rate, and for that purpose 11.0592 megahertz crystal is preferred. We will see that why this value is preferred while we are engaged in serial communication, because it can provide the more precise baud rate that is required for serial communication. So the next thing is that 32 IO lines are available, 2 timers and counters are available. Yes, because it is 8051 microcontroller, only 2 timers or counters must be available on the chip. 6 interrupt sources, considering the reset, we can say 6 interrupt sources are available, 2 priority levels, UART, that means 1 serial port is available, 3 level program memory lock, 4 kilobytes of flash memory is available on the chip, and 128 bytes of on chip RAM. These are the exact specifications which we have studied in the context of Intel 8051 microcontroller. Since Intel has stopped the manufacturing of 8051 microcontroller, and if we want to do something practical with this 8051 microcontroller, we can use this Atmel or Microchip AT89C51 IC. So here I am selecting this IC, I am clicking on OK. Now it is asking me whether we want to copy startup.a51 to project folder. So I am not interested because it is not needed. Whatever is required as a program, we are going to write it. So I am clicking no here. After the project configuration is completed, you may be able to see that here you can see our project has created. The name of project is Square Wave, and one target has been created, and inside this target source group 1 has been created. This source group 1 is empty folder or empty directory right now. So to write any code, we are clicking on this source group 1, and we are right clicking on this source group 1, and we are selecting add new items to group source group 1. When we are selecting add new items, so we are here at this prompt. Here we can create or add C file, C++ file, ASM file, that is assembly language file, or any header file if we are working on any project, .h extension header files are also available, or any text file we can include. So here we are interested in writing assembly language code. So I am selecting .asm file or ASM file, that is assembly file here. KEIL Microvision is taking assembly file extension at .a51. Generally, this extension is also known as .asm. So here I am giving the name of my file and I am giving the name main. So this is the location inside my test1 project. I am going to save this main file. So I am clicking on add. If we are clicking on this plus icon of source group 1, here we can say that main.a51 is available and this main.a51 file is available here also. This is the text editor. This is the place where we are going to write the assembly language program for our 8051 microcontroller. So the first instruction that is required, remember the problem statement is we are going to generate a square wave with any general purpose input output port pin. So the first instruction is required the assembler directive. I am writing with cap locks, and it hardly matters if you're writing without cap lock or you're writing in lowercase letters, it is perfectly okay. So I am writing org space 0000h. That means org is the assembler directive, and this assembler directive, let me try to zoom it a little bit. Okay, so org 000h, org is assembler directive, and assembler directives are the keywords which provide direction to assembler. Assembler generally understands the pattern or the main features that you want to include in your program, like you want to store this instruction at particular memory location, or you want to give a variable a value. So we can use different assembler directives. Generally used assembler directives are org, and the meaning of org is origin. We want to our program origin from memory location 0000h. Since we are not using any interrupts here, so we can skip the interrupt vector table that we will discuss in later videos. So here I can write the very first instruction of my code. So let's give it a label main, and we are here to generate a square wave. Square wave means if we are talking about port 2 pin, that is P2.0. So at P2.0 pin, we want to generate logic level low for a certain time. Then after that certain time, we may be interested in generating logic level high at that P2.0, and we want that this pin should remain at logic level high for a certain time, and we want to repeat the same scenario continuously forever. So this is the way how we are generating the square wave with P2.0 pin of our 8051 microcontroller. So to clear any bit, or if we are talking about P2.0 pin and we want it to remain at 0 logic or low logic, or we want 0 volt at this particular pin, we can clear this bit. To clearing any bit, we can use the instruction CLR, and which pin we want to create is P2.0. So this is the first instruction, and this instruction will clear the P2.0 pin. We want this pin to remain in logic low level for a certain time, and microcontroller is still active. So we need to perform or execute some other task for that particular time. This is called time delay operation. To generate a delay, we can use the concept of subroutine. Subroutines are basically some special programs which may be called in your main program whenever they need it. To call the subroutines, I am using a call instruction, that is absolute call. The range of absolute call is 2 kilobyte. Like from where we are executing a call or absolute call, the subroutine can be stored within the range of 2 kilobyte memory locations. And let's name our subroutine delay. Delay is the name of my subroutine, and it is also known as label that we will use when we will define the subroutine of our project. Then again, let's say that delay amount has been completed, like delay has completed. Now the time to execute next instruction. To execute the next instruction, we may use set bit. That means now we want to put P2.0 at logic level high, or we want to generate 5-volt voltage at P2.0 pin. For that particular reason, we can use set bit instruction, because this instruction is going to set that bit, and in assembly language or in assembly, set bit means we want to put that pin or bit at logic high, that is 5-volt in our case. So we want to set bit P2.0. This instruction will make P2.0 pin at logic level high. Again, if we are interested in generating a square wave, then it is required to stay on this logic level for a certain time or equal time that we stayed when the bit was 0. So again, we are calling a call delay. Again, delay function will be called. After that delay will be over, what is needed? Because we want to generate a continuous square waveform, we need to create a indefinite loop. In assembly language, indefinite loops can be created with the help of unconditional jump instructions. So here I am using S jump instruction, that is short jump. The range of short jump is 128 or 127 bytes in both directions. Short jump, and we want to jump at the level sorry, which is named as main. So this is our main program. Let me arrange this program so that it will start looking good and more readable format. Arrange this with using tabs. Okay, so now easily we can see that what is going to happen here. Our program will start execution from this main label, and this main label, the first instruction is clear P2.0. Your P2.0 pin will be put on logic low, and you are calling additional subroutine, and one subroutine that is named as delay, and the delay operation will be performed, and till that time P2 will remain at logic low. After delay operation will be completed, then we are putting P2.0 at logic high, and again we are engaging our microcontroller with some delay operations or delay execution, and at that time, till that time, P2.0 will remain at logic high. And after this delay is completed, again we are jumping to the main and making this P2.0 0, and again 1, then 0, then 1, and this is the way how we are going to generate square waveform at P2.0 of our microcontroller 8051. The next thing, that what are the instructions which we are going to use in delay operations. So let's say that we want to store our delay subroutine at some another memory location. This memory location can be defined as org, that is again assembler directive, and let's see, we are saving this subroutine at 50H memory location. So I am writing org 0050H. At this location we are putting the label delay, and when we are putting label delay, we need to write some instructions here, because whenever we are calling delay subroutine, a call delay instruction, then program control will be transferred to this delay label, that is at memory location 0050H. In the delay, we generally do, if we are not constrained with the accurate or most precise timing calculation, then we can put any value into any register, and we can decrement that value and check whether this value is 0 or not. So we are engaging our microcontroller in decrementing the register value and checking whether it is 0 or not, and thus we are basically wasting the machine cycles of microcontroller, and these wasted machine cycles are termed as delay produced with the microcontroller. So we are using one register, that is move R0 instruction. I am using register R0 is used, and we are moving one value immediate number to this register R0. So let's say that this number is 10 here, 10 in decimal, because I am not writing H. If I am not writing any H after this number, that means it is in decimal. And in hexadecimal, this number can be represented as, you can easily calculate what it will be, or I will show you when we will try to debug this program. And here I am writing one instruction D, J and Z, that is decrement then jump if not equal to 0. What this instruction is doing, if I am putting R0 here, then this instruction will decrement R0 register and check whether after the decrement this register becomes 0 or not. If it is not equal to 0, if this instruction is running first time and the value of R0 is 10, when this instruction will be executed, R0 will be decremented and the new value of R0 is going to be 9. Definitely it is not equal to 0, it will make a jump. So I said jump here, and I don't want to do any other task, so I am putting label here with this instruction only. Let me quickly arrange these things so that again this will look more readable format. So what we are doing, we are basically putting one value into the register, and we are decrementing that value and checking whether this is 0 or not. If it is not 0, then again we are decrementing that value. So in simple words, I can say that I have executed at least minimum 10 machine cycles of this 8051 microcontroller. This is the amount of delay that we can generate, and if it is good for us, then the last instruction of any subroutine is the return instruction. This instruction basically prompts us to return into the main program. So I have written return instruction. So our subroutine is complete by now, and the last instruction of any assembly language code should be end. So that again, end is an assembler directive, it is not an instruction, and it tells the assembler that our program is not available beyond this line. The assembler will read only this much of program. So I have written one small code. That code is responsible to generate a square waveform, and in this code we are handling with input output ports. Generally we are working with the output behavior of the port, and the pin that we have selected in our example is P2.0. So here again I am explaining P2.0, we are putting it at logic level 0, then we are generating a delay, and here is the delay algorithm. Like in delay, we are putting a value into a register and we are decrementing that value until that value is 0, and if that value is become 0, then we are returning into the main program. And the next instruction that we are going to execute is set bit P2.0. This will put P2.0 at logic level high. Again we are executing the delay subroutine, and we are continuing this operation forever. Let's save this program, and to generate the hex file or the output file of that file, that we can store this file into our program memory of 8051, we need to do certain modifications here. I am selecting a target 1 and right clicking on target 1. We are getting an options for target 1. These are the options of target 1. By default, this IDE is having 24 megahertz of clock frequency, but since I have told that for optimum performance we can use 12 megahertz, so I am using 12 megahertz of clock frequency here. And in the output section, we need to click or select this create hex file option. This will create the hexadecimal file or hex file which is having the opcode of all the instructions. I am clicking on OK, and after clicking on OK, I will build this program. You can select build option if you are doing it first time, or you can select rebuild all target files. So I am selecting build, and if you can see, build started. project name is square wave, build target, target 1, and linking is done, program size, data and the code, and creating hex file from this file. So that means that our hex file has successfully created and there are no errors and no warnings available inside our code. This is the important message. If there is any error, then we need to troubleshoot our program. If there is any warning, you can ignore those warnings as well. So this is the way how we can write the program, but now we are interested in knowing that how this program is running. So in the KEIL Microvision IDE, we can do a debug session or we can do debugging of our project as well. And if we are interested in debugging, here a small red color icon with D is available, shown here, and here you can go into the debug section and start stop debug session. So I am starting debug session. This is coming up with a warning that I am using the evaluation version. So in this evaluation version, the maximum code limit is 2 kilobyte, and it's not a problem for us because we are writing assembly language programs, and most of the time this program will be under this limit. I am clicking on OK. So this debug console has been opened. Here you can see this is your program. This is disassembly window that I will explain you very soon. These are the status of registers. Here you can say that our microcontroller has just started and all registers R0 to R7, these registers are basically representing memory bank 0, because we haven't configured any memory bank using the PSW register. So default register bank, default memory bank 0 is active. So R0 to R7 are the registers from memory bank 0. Then the system registers like SFR registers we are talking about. A register is 0, B is 0, stack pointer is 7 and DPTR is 0, program counter is at 0000H. This shows then whenever our microcontroller is powered up, the default location that microcontroller is going to start the execution of program is from memory location 0000H. That is the main reason we start our program with org00 assembler directive. So let's debug this program. Here are the options. You can run this program as a whole and you may be able to see the result of your assembly language code, or you can run this program step by step. So first we'll run this program step by step, and for that purpose let me open the analyzer window. Here is the icon of analyzer window, and quickly set up the port. The port I am clicking here to set up. The port pin is P2.0. Click enter here and this port has been set up. Now I am again clicking on this P2 port and it is showing me the analog display type, but we are interested in bit display because we are making changes only on a particular bit, that is P2.0, and the color you can change. Red is good for me, so I am not changing it, and I am closing this window. So this is a small logic analyzer window that is available to me here. So let's run first instruction. So here I am pressing F11. First instruction that is executed is clear P2.0. So P2.0 pin is 0 now. If you want to see the status of peripheral, you can come here in the peripheral option and see the output port, port 2. Now you can see that port 2 0 bit is cleared. If there is a tick mark, that means this port is set, this pin is set, and if there is no tick mark, that means this pin is cleared. So next instruction I am going to execute a call delay. After a call delay, you can see here that stack pointer is incremented by 2 because stack pointer, stack memory, inside the stack memory we have saved the address of next executable instruction, that is set bit P2.0, and our program control is transferred here at delay. Still no other significant changes here. Next let's run the next instruction. Move R0 comma hash 10, that means we are transferring the value 10 into the R0. Here you can say that R0 value has become 0AH, that is the hexadecimal equivalent to decimal number 10. So the next instruction I am going to execute DJNZ R0 here. So here you can see that R0 has been decremented by 1. The new value of R0 is 9, and again the program program control is on the same instruction because it is not 0. It has jumped at the same location. So again I am clicking program. You can see the change in R0 register. It is 08, then 07, next instruction 06, next execution 05, next 04, then next 03, then next 02, 01. If this time I will execute this instruction, this R0 will become 0 and this jump is not going to happen. So here it is good to see that R0 has become 0 and the next instruction that is going to execute is return. So when return instruction will execute, we will pop out the values or the address which was stored inside the stack memory, and this stack pointer register which is available at 09 will eventually decrement by 2 and it will become 07. So let's execute the next return instruction. Here you can see that the stack pointer has become 07 and now we are at set bit p2.0. The next thing is again next instruction is executed. Now you can see that this port 2 pin is set. Here the value is going to the high level. Let me zoom in this thing. You can see here that approximately 26 microsecond delay we have produced. 26 microsecond delay has been produced, and again I am executing instructions one by one step at a time, and now R0 is going to become 0. Next instruction execution, and again I am on the main. So here you can see that our program is generating a square wave. Let's run this program in continuous mode and see that how this square wave is looking like. So I have clicked on this run button, that is F5, and here you can see a square wave has been generated on P2.0 pin. If you want to zoom this waveform, you can use the controls from here and zoom out or zoom all. Actually the delay between these two events like set bit and clear bit is very small. So if you are zooming all, then it will look like a dark color picture. So this is the way that how we can write assembly language program using 8051 microcontroller and KEIL Microvision IDE, and how we can test this program using this debug method or debug console available inside the 8051 or KEIL Microvision IDE. So let's stop the execution of this program first, and you want to study anything, you can go here and see the values. Let's stop the debug session. So now we are sure that our program is going to run perfectly well on 8051 microcontroller. So let me quickly show you the other files which were generated. Our folder was test1, and inside this test1, these are the files which have been generated. This is the Microvision project file, and this is the main file, that is assembly language file. If you wish to open this file, you can go with any text editor program. I am selecting here the notepad, and this is the assembly language program that we have written for our project, that is square wave generation. Let me close it. The important thing is object folder, and inside this object folder there is a hex file available. Let's see that how this hex file is looking. Again I am opening this with notepad, and here you can see this is the format of hex file. Only the hexadecimal numbers are written here, and these are the opcodes of the instructions which we provided for 8051 microcontroller. The next thing is object file we have seen, and the listing. Inside the listing, the important and the most appropriate file that a programmer should use for debugging purpose is the list file. So let's see what is inside the list file. I'm again opening it with Notepad, and this is the list file. Here you can see in this list file what is available, some details of your assembler and your IDE. This is the program, and these are the lines of your program, and these are the opcodes of your program. The C2A0, 1150, D2A0, these are the opcodes, and these are the memory locations where your instructions are saved. So by looking only the list file, we may be able to find the exact location of our instructions where these are stored inside the program memory of microcontroller. We may be able to see the opcodes of our instructions like they are listed here, and also these are the labels like main, delay, and here. So what are the memory locations of these labels? We may get the information of about memory locations of these labels from here. So we know that main is having the memory location 0000H, that's good, and we know that at memory location 50 there is a label of delay, so delay location is 50H, and this instruction is taking 2 bytes, move R0 comma hash 10, so 2 bytes have been consumed, 50 and 51. The next instruction here, DJNZ R0 comma here, is stored at memory location 52. So this here label is having the memory address of 0052H. So this is the list file that we can use for analysis purpose or the debugging purpose, or if we want to share our project with anyone, we should ideally be share this list file with the person. That's it, guys. Now today I've shown you that how you can write assembly language program for 8051 microcontroller, and in the next video we'll see more assembly language programming and the peripheral interfacing with 8051 microcontroller while using the KEIL Microvision IDE. And for some projects I'll also try to use the Proteus simulation software so that I can show you the working simulated hardware with 8051 microcontroller. Till then, stay safe, stay happy. Thank you.